Looking at the architecture of a modern large language model, you see a capacity that depends on enormous, dense matrices of continuous decimal parameters. The structural problem with this design is that learned information remains distributed across millions of opaque, private weights. Once a fact is learned, it becomes trapped within this web, making it almost impossible to isolate or extract. This creates a massive computing debt. Teaching a traditional model one single new relationship often requires a global readjustment of these massive matrices through backpropagation. Every connected node must recalculate. This occurs because standard models enforce a hard separation between the data being processed and the logic governing it. Tokens are converted to embeddings, while the instructions live in the parameters, requiring constant translation between the two. As long as knowledge remains locked in these globally dependent, continuous matrices, true continuous learning and instant knowledge transfer between models will remain computationally unscalable. The Aurora project tests a radical alternative. It investigates whether intelligence can be organized as discrete, compositional, and verifiable structures, bypassing probabilistic approximations entirely. To achieve this, Aurora discards continuous decimal weights. It replaces them with a minimal, discrete vocabulary. The architecture relies on homoiconicity, a principle where data, knowledge, instructions, memory, and decisions are all expressed using the exact same structural units. This enables a distributed network where a single node can synthesize a newly learned relationship locally, verify it, and instantly share it with another node without a retraining run. By unifying the structure of information and operation, Aurora attempts to build an AI that never has to recalculate what the network has already comprehended. This is the trit, the atomic unit. The architecture abandons binary bits and decimal floats, operating strictly on a ternary system. 0 and 1 represent determined states. The value 2 represents an open, undetermined relationship outside the current space. Incorporating this open state into the base vocabulary removes the need to approximate the absence of knowledge with continuous decimal numbers. This leads to the TriGate, the core operator for the entire system. It calculates a result by running a ternary majority function across operands A and B and a mode M to produce a result, R. The TriGate uses constraint C to change which cell is open without switching algorithms. In inference, it solves for emergent result R. To learn, it reverses, solving backward for mode M. In deduction, it solves for a missing operand B. Treating inference, learning, and deduction as three orientations of the same mathematical relationship allows Aurora to bypass independent training algorithms and global backpropagation. Scaling up, the architecture groups three trits into a triplet, the minimum unit of structured information. Each slot gets a role: structure, function, and form. Structure selects function, leaving form as the remainder. This logic scales into a kera, taking three distinct triplets to entangle them. Their internal forms are processed circularly through three standard TriGates to validate their geometric relationship. Once validated, it projects a brand new triplet of knowledge upward. This new triplet contains three variables: DO, the next step, DE, the state of coherence, and DS, the formal emergent result. Because a kera's output structure is identical to its inputs, this mechanism can be stacked indefinitely, building complex intelligence without translation layers. Following a strict 1-3-9 fractal progression, that emergent triplet instantly slots into the corner of a larger kera, connecting to three more to form a branching structure. In this architecture, a tensor is a hierarchical composition of recursively stacked keras. The system governs itself without an external loss function. Upper layers process lower outputs, synthesizing three control signals. The RD signal mathematically determines whether the current relation requires learning, inferring, or deducing, based strictly on the emergent logic from below. The RC signal evaluates congruence, declaring if the proposed relation is coherent, contradictory, or still ambiguous. This establishes a localized learning loop. If a relation is coherent, computation stops. If contradictory, compute resources are diverted strictly to the nodes causing the failure. Metacognition, knowing how to decide and what to learn, emerges from the exact same fractal logic gate that processes the data. It requires no outside algorithm. When a tensor fully closes, it slides out of the active processing window and drops into the local dictionary. This is an active operational layer housing closed, reusable structures. The core rule is learn once, solve later. When a known structural context reappears, the system refuses to rebuild the logic from scratch. If an incomplete tensor arrives, the system queries the dictionary in deduction mode. It pulls up saved candidate tensors until one matches the structural gap and snaps into place. If multiple candidate tensors match, they compete via re-execution. The system prioritizes the tensor that successfully closes the current context. When a successful sequence closes, it is minted as a single complex token, called lexicalization. This allows the node to skip those steps in the future. Preliminary testing shows that processing cycles drop drastically as the dictionary fills, restricting active computation strictly to novel anomalies. Traditional models push data through every parameter layer for every query. An Aurora node organically accelerates by permanently caching its own verified deductions. Looking at the vast, distributed network, you essentially see the local dictionary scaled up to an entirely higher level of operation. This introduces the reach signal, or RO. When a node encounters an open relation it cannot solve locally, it packages that open structural relation and routes it to a specialized node on the network. The requesting node transmits the precise structural relation required for deduction, rather than raw data or a standard text prompt. The receiving node uses its domain-specific dictionary to deduce the missing tensor, sending the closed structure back. Because knowledge transmits as a discrete sequence, the requesting node runs the logic locally. Verifying the structure closes, it locks the knowledge into its own dictionary. Network topology evolves naturally as nodes acquire semantic reputation based on their ability to successfully close specific types of structural queries. This peer-to-peer sharing of verified logic bypasses the multi-million-dollar retraining runs required to update modern monolithic language models. The Aurora architecture organizes machine intelligence as a unified fractal system, ensuring the network never spends resources recalculating what it has already comprehended.